Good morning, students. Myself, Vijay Shankar from EC Department, Chevron Engineering College. Today, we are going to discuss about another topic in the microstatics, that is the Maxwell's equation derivations. This is actually the fourth unit is the second part, the Maxwell's equation, the time varying fields. Okay, the derivative part of the Maxwell's equation. The Maxwell's equation. The static electric field E bar can exist without any magnetic field H bar, demonstrated by the capacitor with the static charge Q. Similarly, a conductor with a constant current I has a magnetic field H bar in the absence of the electric field E bar. But in the case of time varying fields, E bar and H bar cannot exist without each other. But in the case of the time varying fields, in the static field, E bar can exist without the magnetic field H bar. Okay, but in the time varying fields, E bar and H bar cannot exist without each other. Okay. The Maxwell's equations are nothing but a set of four expressions. You see here, my students. A Maxwell's equations are nothing but a set of four expressions derived from Ampere's circuit law, Faraday's law, Gauss law for electric field, and Gauss law for magnetic field. These four expressions can be written in the following forms: point form or the differential form, and second one is the integral form. The first one is Ampere's circuit law. Nothing but is a modified Ampere's circuit law, Faraday's law, Gauss law for electric field, Gauss law for magnetic field. Okay. Like what is the Ampere's circuit law? The differential form is del cross H bar is equal to J bar. That is equal to JC bar plus JD bar. You can derive this expression. And Faraday's law, del cross B bar is equal to, on the B bar, my dear friends, E bar is equal to dou B bar by dou T minus. See here the electric field and related with the magnetic flux. Okay. And similarly, here also the JC means sigma into E bar plus JD bar, displacement current density, dou D bar by dou T. Nothing but epsilon into E bar by dou T. So the H bar is related to the electric field. Means magnetic field intensity is related to the electric field intensity, and electric field intensity is related to the magnetic flux density. You see, in the time varying fields. Got it, my dear students? E bar and H bar cannot exist without each other in time varying fields. What is the Gauss law here? Gauss law for electric field is del dot D bar is equal to rho V. These are all, that is a differential form, my dear students, a differential form or the point form. And Gauss law for magnetic field is del dot B bar is equal to 0. These four we can call it as a set of four expressions derived from Ampere's circuit law, Faraday's law, Gauss law for electric field, and Gauss law for magnetic field is called as a Maxwell's equation. And these expressions can be write in the form two forms. One form is the integral form, another form is a point or the differential form. Okay. Let we go for the derive the first equation, the first Maxwell's equation, the first equation according here, the Ampere circuit law. According to the Ampere circuit law, the line integral of magnetic field intensity, H bar around a closed path is equal to the current enclosed by that path. Okay, my dear students. So see the H bar dot DL bar is equal to I enclosed. And what is I? Replacing the current by surface integral of conduction current density J bar over an area bounded the path of integration of H bar. we get more general equation as I is equal to J bar dot ds bar. J bar dot ds bar. The above expression can be made further general by adding the displacement current and the current density. J bar is equal to JC bar plus JD bar minus 2. These are JC and the dou d bar by dou t is the JD. Okay. Integral H bar dot dl bar is equal to the surface integral. This is a line integral. Surface integral JC dot JC plus dou d bar by dou t dot ds bar. Okay. The Maxwell's equation derived from the Ampere circuit law. This equation is an integral form in which the line integral of H bar is carried over a closed path bounding the surface S over with the integration is carried out on RHS. In the circuit theory, the closed path is called a mesh. Hence, this equation considered above is called the mesh equation or the mesh relation. So forget about that. The line integral is converted to the surface integral. We can take the H bar as a del cross H bar dot ds bar. Del cross H bar dot ds bar, and the right hand side already there in the surface integral. So both sides are surface integral only. Then the integral form is integral H bar dot dl bar is equal to surface integral J bar dot ds bar or J bar JC plus dou d bar by dou t dot ds bar. So this becomes a del cross H bar is equal to J bar, nothing but JC bar, JD bar. JD is a dou d bar by dou t. Okay. Del cross H bar is equal to J bar plus dou d bar by dou t. The above equation is a point form or the differential form of the Maxwell's equation derived from Ampere's circuit law. Derived from Ampere's circuit law. Next, second, now the considered a Faraday's law which relates electromotive force induced in a circuit to the time rate because of decreasing of the total magnetic flux linkages. In general, we can write as E bar dot dl bar is equal to E bar dot dl bar is equal to minus of dou b bar by dou t dot ds bar. Dou b bar by dou t dot ds bar. In the right hand side is a surface integral. Left hand side is a line integral. Okay. This equation we derive from the actually the V is equal to minus integral E bar dot dl. Got it, my dear students? V is equal to that potential V, we can change that as a dou b bar by dou t dot ds bar. Okay. So left hand side is converted to the line integral to the surface integral by using the Stokes theorem or the Divergence Theorem. Del cross E bar dot ds bar, and in the right hand side minus integral dou b bar by dou t dot ds bar. So both sides the surface integral only. Remove that surface integral, del cross E bar is equal to minus dou b bar by dou t. As an integral form, E bar dot dl bar is equal to minus dou b bar by dou t dot ds bar. Okay. We'll get this as from the Gauss law of magnetic field. Del cross E bar is equal to minus dou b bar by the dou t. Okay, this Maxwell's equation derived from the Faraday's law expressed in the point form of the differential. And the third one, according to the Gauss law, the total flux out of the closed surface is equal to the net charge with the surface d bar dot ds bar is equal to Q. According to the Gauss law of electric field, Q is equal to d bar dot ds bar. Q is equal to, or the psi is equal to. magnetic, not the magnetic, electric flux. What is a Q? The change of the Q with respect to the volume is equal to volume charge density. dq is equal to rho v into dv, and Q is equal to the volume integral rho v dv. Substitute the Q as volume integral rho v dv is equal to integral d bar dot ds bar. So integral d bar dot ds bar in the left hand side is equal to right hand side we have the volume integral rho v dv. So change the left hand side as in the volume integral, that is volume integral del dot d bar into dv is equal to integral volume integral rho v dv. So both sides of volume integral, remove that volume integral, we'll get the del dot d bar is equal to rho v. So differential form or the point form. Okay. So del dot d bar into dv is equal to integral volume integral rho v dv is integral form. This equation is called the Maxwell's equation for the electric field derived from Gauss law expressed in the integral form. Assume the volume of volume for the integration on both sides, so del dot d bar is equal to rho. This Maxwell's equation for the electric field derived from the Gauss law, which is expressed in the point form or the differential form. It's a point form of electric Gauss law for electric field and integral form of the Gauss law for electric field. Now the last one, for the magnetic field, the surface integral V bar over a closed surface S is always a 0 due to the non-existing of a monopole in the magnetic fields. So integral V bar dot ds bar is equal to, actually it's a phi. Integral V bar dot ds bar is equal to phi. For monopole, the phi is a 0. This Maxwell's equation, this is a Maxwell's magnetic field equation expressed in the integral form. Surface integral is converted to the volume integral. Del dot V bar into dv is equal to 0. Is equal to 0, my students. So right hand side is a 0, means we can no need of the volume integral. Del dot d bar is equal to del dot b bar is equal to 0. It's a point form of the Maxwell's equation. So using the divergence theorem, the surface integral is converted to the volume integral. Del dot b bar into dv is equal to 0. Del dot b bar is equal to 0. Actually, the finite volume dv is not at all equal to the 0. Only you can keep that del dot b bar is equal to 0. It's not the surface integral, my students. It's a volume integral. Okay, this is the differential form of form or the point form of the Maxwell's equation derived from the Gauss law applied for the magnetic fields. Okay, the summarized of all the 4 Maxwell's equation, the differential form and the integral form. For Faraday's law, del integral E bar dot dl bar is equal to minus surface integral dou b bar by dou t dot ds bar. Dou b bar by dou t dot ds bar. And integral form, the differential form is del cross E bar is equal to minus dou b bar by dou t. Here the right hand side the surface integral, left hand side the line integral is converted to the surface integral, we'll get the del cross E bar. And second one, Ampere circuit law or modified Ampere circuit law. So saying that. What is the integral form here? Integral h bar dot dl bar is equal to I plus, you can write that in the inside the jc plus dou t bar by dou t dot ds bar, because I we can write as a j bar dot ds bar. We can write the surface integral dou d bar by dou t dot ds bar and I is there, we added that I, we can represent the j bar dot ds bar, both the surface integrals only. So keep that is a one surface integral j bar plus dou d bar by dou t dot ds bar. Okay, is the integral of h bar dot dl bar, modified Ampere circuit, the integral form. So the left hand, right hand side, the surface integral, left hand side, the line integral is converted to the surface integral, becomes a del cross h bar is equal to j bar plus dou d bar by dou t. Ampere circuit law, the modified Ampere circuit. And the Gauss law of electric field, the integral form, integral d bar dot ds bar is equal to surface integral, not the surface integral, my students, it is a volume integral only. The rho v dv. In the left hand side, the surface integral is converted to the volume integral, that is a del dot d bar. Line integral to the surface means cross product will get, cross curl function. Surface integral is converted to the volume integral means a dot, del dot d bar, and here also del dot b bar on. Okay, it's a very, very important table. The Maxwell's general Maxwell's equation. Faraday's law, modified Ampere circuit law, Gauss law for electric field, and the Gauss law for the magnetic field. Okay, and the conditions, Maxwell's equation for the free space. For the first condition, my dear students, the general Maxwell's equations, the four Faraday's, Ampere's, and the Gauss law for both electric and the magnetic field. The condition, if it is a free space, we have obtained the Maxwell's equation in integral in the point form. Let us consider now the free space as a medium in which the fields are present in the free space is a non-conducting medium. Free space means a non-conducting, nothing but it's a dielectric, simply saying. Having the dielectric in which the volume density rho v is a 0 and the conductivity is also 0. Non-conducting medium means it is not the conductivity. Conductivity is a 0 there. In a free space, it is a non-conductivity. So conductivity is 0 and the rho v is also the 0. So what is a Faraday's law saying that del cross E bar is equal to minus dou B bar by dou T. So there is no any sigma and rho v in this function, is as usual the same thing. And the second one, modified Ampere circuit law, del cross H bar is equal to JC plus JD, my dear students. JC plus JD bar. What is a JC? Sigma into E bar plus JD bar is a dou D bar by dou T. So we are saying here it is a free space means a dielectric. Dielectric is more. Conductivity is very less. Conductivity is a 0. So sigma is a 0 means the first term becomes a 0 plus dou D bar by dou T on. Dou D bar by dou T. So therefore, the Ampere's circuit law, the modified Ampere circuit law in the free space, del cross H bar is equal to only GD bar. That is dou D bar by the dou T only. You see here. Del cross H bar is equal to dou D bar by dou T. And the third one is the Gauss law of electric field. What is the point form? Del dot D bar is equal to rho v. Here in the free space, the volume charge density is also the 0. So del dot D bar is equal to 0. The second and the third one is changes. And the fourth one and the first one is there is no any change in the general Maxwell's equation. Del dot B bar is equal to 0. Okay. It's a point form. What is the integral form? The integral form, nothing is changes in the integral form for the first one. Integral E bar dot DL bar is equal to surface integral dou B bar by dou T dot DS bar. And in the second function, the second, I told that the JC is a 0 because the conductivity is there. So JC is a 0, only we have the JD, dou D bar by dou T dot DS bar. And third equation also, integral d bar dot ds bar is equal to integral rho v dv. Rho v is a 0 here. Rho v is a 0. So second and the third is a changes. Sigma is equal to 0 here. Means JC is equal to 0. And here the rho v is equal to 0. Both are changes. In free space, nothing but it is a dielectric simply stated. And this one is a second table of the Maxwell's equation. And third table, Maxwell's equation for the good conductor. I told that the ratio between of JC by the JD is equal to sigma by the omega epsilon is very much greater than 1 means sigma is very much greater than the omega epsilon. Its conductivity is a more. So good conductor. Conductivity is a more means the rho v is equal to 0. It is clear that it clear from the type of the medium that the conductivity is a very high here. The conductivity is not the 0. So for the good conductors, we can write as JC is very much greater than dou d bar by dou t. Sigma is very much greater than the omega epsilon. And rho v is equal to 0. Now what are the equations we have? One is del cross E bar is equal to minus dou b bar by dou t. There is no any change in this function. And second one is del cross H bar is equal to JC bar plus JD bar. So the JC is very much greater than the JD bar means we have only the JC that is equal to sigma into E bar. The second term becomes a 0 because the dielectric is a omega epsilon or JD bar is very much less than the JC. Okay, the second one is modified and del dot D bar is equal to rho v. Here also the rho v is a 0. In the good conductor, the rho v is a 0. Third one is changes. And the fourth one is there is no any change in the fourth. Del dot B bar is equal to 0 only. Even in the good conductor also, the change occurs in the second and the third one only. First and the second, last, it's not the changes. There is no any change. Del cross E bar is equal to minus dou B bar by dou T. And del cross H bar is equal to only the J bar. There is no any J D bar. Del dot D bar is equal to 0. Del dot B bar is equal to 0. So integral form. Nothing is changes in the first one and the last one, and only the changes occurs in the second and the third. That is integral h bar dot dl bar is equal to I, and I is nothing but j bar dot ds bar. In that j is also only the JC, conduction current density only. There is no displacement current density because there is a epsilon. Dielectric is a 0. And the last one, Maxwell's equation for the harmonical varying the fields. Third table means the fourth table minus 2. General Maxwell's equations. Second one is the condition for the free space. In that free space, conductivity is a 0 and rho v is a 0. And the third table modifying that rho v is a 0 and the epsilon is also 0 because it's a good conductor. Conductivity is a more. So JC is a more compared to the JD. Now the Maxwell's equation for the harmonically varying fields, D bar is equal to D naught into E power j omega naught, and B bar is equal to B naught into E power j omega t. I told dou by dou t is replaced with j omega, simply saying. By using this equation, see that dou bar is equal to D naught into E power j omega t. Now you can write the dou d bar by dou t is equal to d bar into, with respect to the t here, j omega into e power j omega t. Is a d naught master, my dear students. What is a d naught bar and e power j omega t is a j omega into d bar. So here the d bar is there and here the d bar. What is a dou by dou t is nothing but j omega. J omega into d bar and j omega into b bar. So wherever the dou by dou t is there, you can replace that as a j omega 1. In the Maxwell's equation of the fourth table, harmonically varying fields. So the first equation, the point form, del cross E bar is equal to, what is the del cross E bar is equal to? Minus dou B bar by dou T. What is the dou? I replace dou by dou T is the j omega. Minus j omega into B bar. Is a minus j omega into B bar. So B bar is can also represent in the magnetic field mu into H bar. Okay, this is the first one. The second point form, del cross H bar is equal to JC plus JD. What is the JC? Sigma into E bar. What is the JD? Dou by dou T of D bar. Means a sigma into E bar plus dou by dou T replaced as a j omega into D bar. That is equal to sigma into E bar plus j omega into epsilon E bar. Okay, my dear students. Epsilon into E bar. So see here, del cross H bar is equal to j plus j omega into D bar. And sigma into E bar, j omega epsilon into E bar. Both the functions, E bar you can take as a common, sigma plus j omega E bar. This is the second one. Third one, Gauss law for the electric field, del dot D bar is equal to rho v in the D. There is no any changes because there is no any dou by dou T here. And the fourth one is del dot B bar is equal to 0. No changes in the third and the fourth because there is no with respect to the time. Got it, my dear students? So integral form, wherever there is a dou by dou T, you can replace as j omega simply. J omega into mu H bar dot ds bar, and I plus I is a j bar dot ds bar, and j omega dou by dou T, j omega epsilon into E bar. The third and the fourth is the same. Okay. And these general form of the Maxwell's equation table and the free space of the Maxwell's equation table and good conductor table and harmonically varying table. So these four tables are very, very, very important, my dear students, the examination point of view, the Maxwell's equations. And the conductivity current, conduction current density JC is equal to sigma into E bar, and displacement current density JD is equal to dou D bar by dou T. And these are very, very important equation is a further units electromagnetic characteristics 1 and electromagnetic characteristics 2. Simply by heart or logically we can remember this all the equations. We'll get definitely the 16 marks in this the Maxwell's equations one. Remember this general form equation. In the free space, simply wherever you can, rho v is there, give the 0, and sigma is equal to 0 because the conductivity is a 0 here in the free space. Okay. In the dielectric, a good conductor, in good conductor, epsilon is equal to 0. Epsilon is equal to 0 means simply not the epsilon, you can say JC is very much greater than the JD. So we are eliminating the JD, only we are taking the JC only. Okay. And the rho v is also 0 in the free space and the good conductor. Free space means is a perfect dielectric. And the last table, harmonically varying fields, wherever we got dou by dou T, replace j omega. In the first and the second one only, there is a with respect to the time, dou b bar by dou T. Dou by dou T is j omega, and sigma into E bar, but dou by dou T of T bar, dou by dou T is a j omega. Got it, my dear students? And The last topic is remaining. That topic is boundary conditions between the conductor and the free space. We'll continue in the next.